Hello everyone. I welcome you all to this digital classroom for the subject control systems. In the previous lecture, we discussed about rule number 1 to 5 for the construction of root locus. And today, in continuity with that, let us discuss about rule number 6 and 7 for the construction of root locus. Let us look into rule number 6. It is subjected to a special case of point of multiple roots, which is the intersection point of two roots that lies on the real axis. Let me explain this with an example. Let us represent two poles on the S-plane, one at S is equal to -1 and the other pole at S is equal to -2. Making use of rule number 3, first, let us find out the existence of root locus in the S-plane. So let us take a point on the real axis, and if you look into the right side, you have to check for whether do we have any odd number of poles and zeros towards the right. No, in this case we don't have any odd number of poles and zeros. Hence, we can say that no root locus, that is, root locus does not exist, NRL. Now let me take a point exactly in this place and let us look towards the right side. Now you could able to see one pole towards the right. Hence, a root locus exists towards the left of a odd numbered pole. Hence, root locus exists between -2 and -1. Let me write it as RL. And let us take a point here. It might be around -2.5. Now look at the right side and again ask the same question, whether you could able to see any odd number of poles and zeros towards your right. No, we have even number of poles towards the right. Hence, root locus does not exist. Let me write it as NRL. So making use of rule number 3, we have identified the existence of root locus. Now, when k is equal to 0, the location of the poles will be exactly at -1 and -2. As k increases, the poles will be moving in the direction of the root locus. So -1 will be moving in this direction of the root locus. The branch which is emerging from -1 will be moving in this direction. And the branch which is emerging from -2 will be moving in this direction. As k keeps on increasing, these two branches which is emerging from -2 and -1 will meet at a single point exactly on the real axis. That is, the two roots meeting at the same point for a particular value of k. Hence, the two roots meeting at the same point on the real axis for a particular value of k will have multiple poles in that location. That is what it has been specified here in this statement, a special case of point of multiple roots. That is exactly at a particular value of k, two roots will meet at a single point, which is the intersection point of two roots, and that lies on the real axis. Let me continue with the statement. If the branches is leaving the real axis and entering the complex plane, the point is called the breakaway point. So now we have identified that at a particular value of k, two roots intersect with each other and it results in multiple root at a particular location. And now the question is whether the branches is leaving the real axis or entering the real axis. This is what we have to analyze now. In this example, if you clearly look into the movement of the branches, it is very evident here, that is the branches is moving towards this direction. It is trying to break away at this point. And again this branch is trying to break away at this particular point. That is, it is trying to enter the complex plane. The branches is leaving the real axis and entering the complex plane. So when k keeps on increasing, you could able to see all the roads exactly on the complex plane. After reaching this point, if you keep on increasing the value of k, now the roads will try to move from the real axis and it tries to enter the complex plane. These points shows the complex plane. So we can call this point to be as breakaway point. Hence, if there are adjacently placed poles on the real axis and the real axis between them is a part of the road locus, then there exists minimum breakaway point. So this is a prediction. This rule comes out with the prediction that if there are adjacently placed poles, yes, we could able to see adjacently placed poles in this example, and it is on the real axis also, and the real axis between them should be a part of the root locus. Yes, this region between them is a part of the root locus. Then there exists minimum one breakaway point. So you are very sure that there exists minimum one breakaway point. That is a special case of point of multiple roads, which is the intersection point of two roads exactly at one particular value of k. When k starts increasing from 0 to infinity, at one particular value of k, you get multiple routes at one particular location, and that intersection point, we can call it as breakaway. And again, you have to check for this condition which says that the branch is leaving the real axis and entering the complex plane. In this example, the branch is trying to leave the real axis and it tries to enter the complex plane, both the branches which is emerging from both the poles. Hence, you can say this point to be as breakaway point. Hope you could able to understand each and every word specified in the rules has a very beautiful meaning behind it. So you have to be focused and you have to concentrate each and every word I try to convey you. Hence, there exists a breakaway, so I can specify with the arrow mark of the direction of the branches. From this pole, it is moving in this direction. It is moving away from the real axis and it is entering the complex plane. And again, this pole reaches the breakaway point and it is breaking away, moving from real axis towards the complex plane. Hence, a breakaway point exists in this region. Let me continue reading the statement. If the branches is leaving the complex plane and entering the real axis, the point is called the break-in point. So we have another point which is called as a break-in point, and the condition given here is the branches leaving the complex plane and entering the real axis. In continuity with the previous slide which we discussed about rule number 6, now we are going to analyze break-in point. The condition given here is if there are adjacently placed zeros on the real axis and the real axis between them is a part of the root locus, then there exists minimum one break-in point. In the previous case, when we are discussing about breakaway point, the condition given was with respect to two adjacently placed poles, and it should be in the region of root locus. Then there exists minimum one breakaway point. Whereas in this case, if there are adjacently placed zeros in the place of poles, if we have adjacently placed zeros, and if it exists in the region of root locus, then you can say that there exists a break-in point. Let us take an example with two adjacently placed poles in the S-plane. Its location is shown here, and making use of rule number 3, we can mark the existence of root locus, and we know that this region is the existence of root locus, as we know that root locus exists towards the left of the odd number pole. So this is very clear and evident that root locus exists in this region. And if this condition occurs, what has been specified here? There exists minimum one break-in point. Hence, this is the location of both the zeros at k is equal to 0. And when we keep on increasing the value of k, at one particular point of time, we get multiple pole, that is intersection of two roots. That is intersection of two roots, multiple pole at one particular point for a particular value of k. And in this case, this is not going to be a breakaway point. This will be called as break-in point. And we could able to see the moment of branch, which is, and the branches is trying to move from complex plane and it enters the real axis. Hence you can see that a break-in point exists in this region. And the angle will be always exactly 90 degree for breakaway and break-in. Let us take an example and justify this rule. So in this case, we have multiple pole at the origin, s is equal to 0, 0, and we have two zeros in the negative real axis. First, let us look into the existence of root locus. So we know with respect to rule number 3, root locus exists towards the left of odd number of poles and zeros. So if you take two multiple pole at origin, so if you inspect here, exactly at this point towards the right, you could able to see one pole, that is s is equal to 0. Hence root locus exists towards the left. So with respect to this case, you could able to see the existence of root locus in this region. And if you take a point here, and if you look into the right side, it is even number of poles. So root locus does not exist in this region, NRL. And if you take a point here exactly, and if you look into the right, we have a count of 1, 2, 3. Hence it is odd number of poles and zeros. Hence a root locus exists towards the left of it. And I can represent it as RL. And exactly at this location, now you have a count of 1, 2, 3, 4. Hence even number of poles and zeros. Hence root locus does not exist in RL. Once after completing with rule number 3, now we have to predict for the existence of breakaway point and break-in point. With respect to rule number 6, it is very clear that if you have two adjacent poles and if it is in the region of root locus, then there exists a breakaway point. So we can relate the statement with this case in which we have two adjacent poles and it is in the region of root locus also. Hence, one breakaway point exists exactly in this region, that is s is equal to 0 is the breakaway point. And on the other side, with respect to the last statement, if there are adjacently placed zeros. Yes, I have adjacently placed zeros on the real axis, and between them is a part of the root locus. Yes, of course, it is a part of the root locus. Then there exists minimum one break-in point. Hence, in this case, minimum one break-in point exists in this region. Let me represent it with a different color. So here one minimum break-in point exists, and here minimum one breakaway point exists. So a breakaway point between two adjacent poles breaks away, and it is moving from real into the complex plane, and it is trying to enter into the real axis from the complex plane. And on the other side, the branch which is emerging from the other pole also try to move from real axis, that is s is equal to 0, and it is entering the complex plane, break away. And on the other side, it is trying to move from complex plane and trying to reach into the real axis, that is break-in. Hence, let us represent the location here. So minimum one breakaway and one break-in point exists in this location, and it has been highlighted here. And also with respect to rule number 2, we know that root locus always start from a open loop pole and terminate at open loop 0. So if we take this example, as we have p equal to 0, it's a strictly proper transfer function. Hence, two branches which is emerging from two poles has to terminate at 0. None of the pole is going to terminate at infinity. Make a note of it. Hence, in this case, for the pole at s is equal to 0, with respect to increase in k, it reaches at one particular point, breakaway, and it breaks away, and it breaks in, satisfying the third condition of rule number 6, and then it tries to reach the 0 here. And on the other side, the another pole at s is equal to 0, again with respect to increase in k, it reaches the breakaway point at one particular point of k, multiple pole across, and we call it as breakaway, and it breaks away, and it has moved from real axis into the complex plane, and it tries to move from complex plane into the real axis, that is at exactly at the breaking point, and reaches the other 0. So rule number 2 also has been justified here, that is for p is equal to z, it starts from open loop pole and it terminates at open loop 0, which has been justified here. So making use of rule number 6, we have made use of the previous two rules, rule number 3 for existence of root locus and rule number 2 for the starting point and the terminating point of the branches. And now it is very clear with rule number 6. Let us take another special case for the same rule number 6, in which if there is a 0 on the real axis and to the left of that 0 there is no pole or 0 existing on the real axis, and the complete real axis to the left of that 0 is a part of the root locus, then there exists minimum one break-in point. So let us take this example. If there is a 0 on the real axis, so let us mark a 0 on the real axis, and to the left of the 0 there are no poles and zeros existing. Yes, there are no poles and zeros existing in this example. And the complete real axis to the left of that 0 is a part of the root locus. Yes, of course, this complete real axis to the left of this 0 is a part of the root locus which is justifying rule number 3. If these conditions are satisfied, then there exists minimum one break-in point. Hence, there exists one minimum break-in point which has been specified here, break-in, which means that exactly at this location we have a break-in point in which the branches are moving from the complex plane and it is entering the real axis. Let me justify the statement making use of this example. In this example, we have 3 poles and 2 zeros. Let us mark the region of root locus. With respect to the same previous example, we know that root locus exists between these region, and in this region, root locus exists towards the left of odd number of poles and zeros. And also it exists exactly in this region towards the left of the 0, as we have a count as 1, 2, 3, 4, 5. Hence root locus exists towards the left of it. Once after marking the region of root locus, now we have to predict for the breakaway and break-in point. As we have 2 adjacently placed poles and these 2 poles is a part of the root locus, hence we are very sure that there exists a breakaway point. And we have to now check for whether we have any adjacent zeros. In this case, we have an adjacent 0 here, but we have to check again and cross verify with whether it is a region of root locus. No, this is not a region of root locus. Even though we have 2 adjacent zeros here, as it is not the region of root locus, we cannot take it to consideration. And we have to check for another condition in which if there is a 0 on the real axis and towards the left of the 0, there are no poles and zeros existing on the real axis. Yes, I have a 0 and towards the left of the 0, I don't have any poles and zeros on the real axis. And the complete real axis to the left of the 0 is a part of the root locus. Yes. Is it a part of the root locus? Yes, of course, it's a part of the root locus. Then there exists minimum one break-in point. Let me highlight with a different color. That is exactly in this region, there exists minimum one break-in point. Now, having all these predictions in mind, we can plot the branch. From the pole at SS equal to 0, there will be a branch which is emerging from it with respect to the increase in value of k from 0 to infinity, and it intersect at a single point which results in breakaway, which moves from real axis into the complex plane, whereas on the other side it tries to move from complex plane into the real axis exactly at the break-in point. Similarly, the other pole at S is equal to 0 again try to move from real axis into the complex plane, and on the other side it tries to enter into the real axis exactly at the break-in point. And with respect to rule 2, in this example we have number of poles p is equal to 3 and number of zeros z is equal to 2. Hence, out of these 3 open loop poles, 2 poles will try to terminate at 0. That is, the rest of the p minus z, that is 3 minus 2, that is one of the pole will be terminating at infinity. So let us justify the statement. So one of the pole at S is equal to 0 with respect to increase in k will reach at a point for a particular value of k in which we get a multiple pole, that is the breakaway point, and it tries to breaks away, that is moving from real into the complex plane, and then here it tries to break in and it tries to move from complex plane into the real axis, and then it reaches open loop 0. And on the other side, here we have a pole, and this is the location at which k is equal to 0. When k increases, this branch will be moving towards the 0 on the other side, and it exactly reaches 0 when k is equal to infinity. So out of 3 poles, 2 of the poles has been terminated at open loop zeros, and the rest of the p minus z, that is the rest of the pole, will try to break away, and then it breaks in and then try to reach infinity. So we have justified with rule number 2. Hence, in this example, a breakaway point exists in this location between 2 adjacent poles, and a break-in point exists in this location. Justified with rule number 6, and we could able to predict for the existence of breakaway and break-in point with different special cases. Now, we have to exactly find the location of this break-in point. So we have few steps to be followed to calculate the break-in point. Let us look into that. Let me take an example. To calculate breakaway point for given d of s is equal to k divided by s into s plus 1 into s plus 2. Starting from the rule number 1, we have taken the same example. So I request everyone to look into the previous video so that you can get a clear picture about these concepts. So the first step to calculate the breakaway point is to find the characteristic equation. So we know that the characteristic equation is given by 1 plus g of s into h of s equal to 0. Let us substitute for g of s in this characteristic equation. So we get 1 plus k divided by s into s plus 1 into s plus 2, which is equal to 0. Root locus must have a breakaway point which can be found by the following steps. Once after writing the characteristic equation, let us simplify the characteristic equation. Once after simplification, we can obtain s into s plus 1 into s plus 2 plus k equal to 0. For this simplification, I can write the characteristic equation as s cube plus 2s square plus s square plus 2s plus k equal to 0. Now let me represent k, and to the right side let me represent the polynomial of the characteristic equation, that is all the s terms. Then in the next step, let me calculate dk by ds equal to 0. That is, we are going to differentiate k with respect to s. Once after differentiating, dk by ds will be equal to differentiation of minus s cube will be 3s square, and differentiation of minus 3s square will be minus 6s, and differentiation of minus 2s will be equal to minus 2. Equate it to 0. Based upon the power of s, as the power of s is 2 here, we get 2 roots from this equation. So let us solve this expression. 3s square plus 6s plus 2 equal to 0. As the highest power is 2 here, we get 2 roots by solving this equation. So let us solve this equation. Once after solving, you get exactly 2 roots. S1 is equal to minus 1.577 and S2 is equal to minus 0.423. Now we are supposed to find the validity. Once after obtaining the roots for this expression, we have to check for the validity, that is, making use of the rule number 6. If this condition satisfies rule number 6, then we can say that it is valid. The obtained breakaway points is valid. If it is not justifying the statement, then we can say that these breakaway points are invalid. So first, let us plot the poles on the S-plane as shown here. So we have already marked the poles at S is equal to 0, S is equal to -1 and S is equal to -2. And we have applied rule number 2, 3, 4 and 5, and we have found the sigma is equal to -1, the centroid, and we have found the angle of asymptote at exactly theta is equal to 60 degree, theta is equal to 180 degree, and theta is equal to 300 degree. And making use of rule number 6, we can predict the existence of breakaway point. So we can check whether we have any alternate poles and zeros. Yes, we have alternate poles and zeros. Two cases we have. But out of these two, we have to check whether it is in the region of root locus. Then this case becomes invalid. And now we have only one pair of adjacent poles and zeros which is in the region of root locus. Hence, there exists minimum one breaking point. This is by prediction, which justifies rule number 6. Now we have to locate the exact point of the breakaway point on this negative real axis. By following the procedure, we have obtained two locations, one exactly at -1.577 and the other exactly at -0.423. So let us mark -1.577 comes exactly here, and -0.423, it comes exactly here, 0.423. Out of these two cases, as these two adjacent poles is not lying in the region of root locus, -1.577 becomes invalid, whereas -0.423 is between two adjacent poles and it is in the region of root locus. Hence, it is a valid breakaway point. Hence, I can say that as S1 is equal to -1.577 is not on the root locus, it is invalid, and on the other side S is equal to -0.423 is on the root locus. Hence, it is a valid breakaway point, and I have marked exactly -0.423 on the negative real axis. And this is the procedure to be followed, and we can make a note of this. Breakaway point can be in the real axis or in the complex plane. It is not necessary that always the breakaway point has to be in the real axis. It can be in the complex plane also. If you solve few example problems related to root locus, you will get a clear idea about it. So in the coming sessions, you watch the YouTube link from the playlist control systems so that you can have a glimpse on different types of problems related to root locus. Let us move on to rule number 7, which states that the intersection of root locus with the j omega axis, that is on the imaginary axis, at points where the route criterion shows a transition from roots in the left half plane to the roots in the right half plane. So, with respect to rule number 7, we are going to calculate the location of the roots exactly on the j omega axis, which means that making use of route criteria, we know that if the roots are present in the left half of the S-plane, we say that the system is stable, And if it is present on the imaginary axis, we say that the system is marginally stable. And if the roots are present on the right half of the S-plane, then we say that the system is unstable. Let us take an example with two poles in the negative real axis, and it is in the region of root locus. And let us assume that we have two asymptotes. So these are the location of the pole exactly when k is equal to 0. When k increases, there will be a moment in the pole and the branches will be trying to emerge from this point, and both will intersect at one particular as it is valid for minimum one breakaway point with respect to this condition, and it will break away, and with respect to increase in k, it will be moving from real axis into the complex plane, and when k keeps on increasing at one particular point of time, this root will try to intersect on the imaginary axis. At one particular value of k, it exactly intersect on the imaginary axis. And in this case, the system becomes marginally stable. And this is what given here, that the Route's criterion shows a transition from roots in the left half plane to the roots in the right half plane. So making use of Route's criterion, we can find the roots which is intersecting on the imaginary axis. So with respect to rule 7, we are going to calculate the intersection of the root locus with the imaginary axis. And beyond this imaginary axis, if you keep on increasing k, the root try to enter into the right half of the S-plane and the system becomes unstable. So we can say exactly at the root on imaginary axis, k can be represented as k margin, and we can make use of the stability analysis which we have followed previously for RH criterion. And this transition means that the closed loop system is becoming unstable. That's what I told you right now. This fact can be tested by a route stability criterion with k as a parameter, where an incremental change of k will cause the sign change of the element in the first column of the route array. So the steps to be followed here is, we have to write the characteristic equation, then we have to generate the route array. Once after generating the route array, we have to find the range of k. Once after finding the range of k, we can exactly find k margin at which the system is becoming marginally stable. And once after reaching k margin, an incremental value of k which has been specified here. If suppose k margin is equal to 6, and one incremental value of this k value 6.1 or 6.2 will leads to a sign change in the first element of RH array, s power 6, s power 4. If I have this RH array, generated RH array, there will be a change of sign in the first column, which is making the system to be as unstable. And the value of s is equal to plus or minus j omega naught are the solutions of the characteristic equation in the root locus from the characteristic equation 1 plus k into g of s is equal to 0. This is very clear that rule number 7 is completely related to RH criterion. So we have to generate the RH array first, then we have to interpret with the RH array, finding the range of k, and we have to find out k margin at which the system is becoming marginally stable. That is with respect to case 2 in which the complete row becomes 0. If the complete row becomes 0, we know that it is case 2, a special case in RH criterion. We used to take the previous row as an auxiliary equation, and if you solve that auxiliary equation, we get the roots on the imaginary axis, and that gives you the intersection of the root locus on the j omega axis. So this rule number 7 is not new to you, as we have done already with respect to RH stability criterion before. Also, the points plus or minus j omega naught or the points of intersection on the imaginary axis. So whatever point which we have obtained after solving the auxiliary polynomial will be the points on the imaginary axis. So let us calculate the intersection point on the imaginary axis for the same example problem. So we are going to calculate the intersection point on the imaginary axis. For the same example, g of s is equal to k divided by s into s plus 1 into s plus 2. So first step is to write the characteristic equation. Simplify the characteristic equation. We have simplified already with respect to rule number 6. Once after representing the characteristic equation, we have to generate the Routh array, and this is the same plot which we have obtained up to rule number 6. And let us generate the Routh array. So we know to fill up the Routh array for the first two rows, s cube coefficient is 1 and s square coefficient is 3. S coefficient is 2 and we have a constant k. And to fill up the third row, we know to trace the pattern 3 into 2 minus 1 into k divided by 3. Hence we have obtained 6 minus k divided by 3. And the next element will be equal to 0. 3 into 0 minus 1 into 0. Hence it will be 0. And for filling up the last row, we have to trace the pattern 6 minus k divided by 3 into k minus 3 into 0 divided by 6 minus k divided by 3. 6 minus k divided by 3 in the numerator and in the denominator will get cancelled out. Hence we get 6 here. And I have told you that there will be a shift diagonally, and finally for the last row we will be getting the same constant which is specified in the characteristic equation, provided if this element is 0. Now let us find the value of k. For the row s to the power 0, k greater than or equal to 0. And for the row s to the power of 1, we have 6 minus k divided by 3 greater than 0. Hence, 6 minus k greater than 0. Therefore, minus k greater than minus 6. Hence, k greater than minus 6. Therefore, I can write k lesser than 6. And k is ranging from 0 less than k less than 6. Which means that the system is stable between the range for k ranging from 0 less than k less than 6. If I substitute k margin is equal to 6 in this expression, the first element will be 6 minus 6 divided by 3, that is 0. Hence this row becomes a complete 0 row. And it leads to a special case 2 in RH criterion. If it is a complete 0 row, we have to take the previous row and represent it as an auxiliary polynomial. And if you solve that roots, you will get few roots on the imaginary axis, which is making the system to be as marginally stable. Let us represent the auxiliary polynomial, which is given by, from this s square row, we can write it as 3s square plus k equal to 0. Once after representing the auxiliary polynomial, we can simplify this by substituting for k is equal to 6 in this expression. 3 square plus 6 is equal to 0. Hence I get 3 square plus 6 is equal to 0. By solving this equation, 3 square will be equal to minus 6. S will be equal to plus or minus J 1.414. So we have obtained two roots on the imaginary axis and it has been marked here exactly, which is making the system to be as marginally stable. So we have done with rule number 7 and we have followed the steps to be followed to find the intersection point on the imaginary axis. Starting from rule number 1 to rule number 7, we have taken the same example. So let us look into the final plot of the root locus also for the same example. After examining rule number 1 up to rule number 7, now there is enough information to draw the root locus plot. Almost we have drawn 80% of the root locus. Only thing left out is to plot the final graph. We have marked with the intersection of the root locus on the imaginary axis and we have marked with the breakaway point and we have plotted all the region of root locus highlighted in yellow color and we have marked the centroid sigma is equal to minus 1 and we have marked all the angle of asymptotes, one at 60 degree, one at 180 degree and the other one at 300 degree. In this example, with respect to rule 2, which has been defined already, we have a number of poles as 3 and number of zeros as 0. All the 3 poles, that is P minus Z, 3 minus 0 poles. The branches which is emerging from these 3 poles will be terminating at infinity. This is what we have defined in rule number 2. Let us justify the statement. One of the pole which has a location at minus 2 is going to terminate at infinity as the asymptote is guiding exactly at 180 degrees. And if you look at the other two pole, one at minus 1 and other one at 0, at k is equal to 0, these poles will be exactly at 0 and minus 1. Once after increasing the value of k, there will be a moment with respect to these poles on the region of root locus. And on the other side for this pole, there will be a moment here in this region. And both will be meeting at one single point for a particular value of k, that is multiple root occurring here. And we can say that there is a breakaway point as it is between two adjacent poles and it is in the region of root locus. Once after breakaway point occurs, we know that these branches will break away and move from real axis into the complex plane. Similarly, for the pole at 0 also breaks away and enters the complex plane. And with respect to the final rule number 7, in this case, when we keep on increasing the value of k, it try to reach and it will intersect exactly on the imaginary axis. In this case, k margin is equal to 6. We could able to see the intersection of the root locus on the imaginary axis. And when k greater than 6, this root locus try to reach the right half of the S-plane, which makes the system to be as unstable, and it reaches infinity when k reaches infinity. And this shows the complete plot. Let me show you the proper sketch of it. It is shown here how the branches are emerging. It is shown here how the branches are emerging and reaching infinity. And it is shown with respect to arrow mark. This is the complete root locus. the moment of the poles which is branching here and emerging here, and for the other pole the second branch and the third branch. As we had P minus Z asymptotes, 3 minus 0 asymptotes, we could able to see three branches which is reaching infinity, and these asymptotes are the one which is guiding these branches. As we have taken an example with roots on the real axis, rule number 8 which is left out here becomes not applicable in this case. So let us discuss about rule number 8 in the next lecture. In the next lecture, let us discuss about rule number 8 which is applicable for complex poles. Thank you.